Hello everyone, my name is Adriel and I'm going to present an article entitled Milling and Magnetic Abrasive Finishing of Directed Energy Deposited 316 Stainless Steel, which was co-authored by Iago, Professor Heraldo and Professor Reginaldo. First, additive manufacturing, AEM, is a technology for building three-dimensional parts from layer to layer, which direct energy deposition, DED, being one of the techniques that stand out for metallic component. Each process combines material feedstock and energy for layer-by-layer deposition, hence formation of the part. However, both dimensions and surface quality of the parts are relatively poor, requiring post-process operation to overcome those limitations. Depends on the application of the component. Traditional machining process, for example, milling, or even some advanced finish process, for example, magnetic abrasive finishing, MAF, are therefore necessary for the obtaining of the desired functional performance. As milling is a well-known process, on the next slide I will explain a little bit about the MAF process. MAF mixes magnetic abrasive particles and abrasives in a magnetic field between poles and the workpiece itself. The material is slowly removed through magnetic forces and relative movements, improving surface quality. Regarding post-process operations of parts made using additive manufacturing, it is necessary to study manufacturing process chain in order to reduce the steps involved and consequently reduce manufacturing costs and time. It is in this scenario that this article intends to contribute scientifically. Therefore, this study aims to evaluate the impact of milling and MAF operations in the surface quality of 316L stainless steel produced by DED, as well as the effects of the process on surface morphology and roughness. So, a manufacturing sequence was proposed and involves AM, which was DED, milling, and MAF, successfully applied for improving surface roughness up to nanometer levels. Regarding DED, workpieces shaped as rectangles were deposited using a zigzag strategy. Other conditions are shown on the slide here. After deposition and milling was carried out, 3 different cutting speeds values were tested: 300, 400, and 500 meters per minute. The parts machined under those conditions will be referred to as M300, M400, and M500 respectively. So after milling, MAF was carried out. 3 neodymium magnets were used to create the magnetic field, rotating at 500 RPM. A mixture of iron particles and abrasive slurry was made. Each sample was polished at 5, 10, and 15 minutes, respectively. So the parts will be referred to as MAF5, MAF10, and MAF15. This figure shows the general aspects and the surface morphologies of parts after each manufacturing process. After DED, the contours of deposition beds are visible and some voids and the adherent powder particles were present on the surface, worsening the surface quality. After milling, the surface has typical cutting marks, which is inherent to the process. Finally, the surface after MAF process has a mirror appearance in which the milling marks have been smoothed and even removed. A new texture has arisen due to the abrasive workpiece interaction, showing fine directional patterns parallel to the abrasive slide direction. This figure shows the roughness values obtained after each process. for DED, the three conditions of milling, and the three conditions of MAF. It can be seen that the surface roughness RA was reduced from 56 to 0.08 microns by M300 and to 0.03 microns by MAF15, indicating more than 99% improvement. Regarding the RZ values, there was a reduction from more than 240 to 0.56 microns by M300 to 0.23 by AMF in all conditions, also showing more than 99% improvement. These high roughness values of the parts manufactured by DED is due to several factors, such as deposition beds morphology and geometry, presence of partially melted powder particles adhered to the surface, and others. During milling operation, despite the presence of some edge marks, the roughness values were provided at nanometer levels. After MAF, surface quality was improved, in which roughness values were minimized and surpassing those achieved by milling. The line in black represents the processing route adopted by a reference study in the area, published by Yamaguchi. 4 hours of processing time were spent on a reduction of RZ from more than 100 to 0.1 microns. So the line in red represents the processing route adopted in this study. The RZ of the parts presented here are more than twice of that reported by Yamaguchi. Under the same processing conditions, near 5 hours and a half or more would be necessary for the achievement of the same surface quality. However, using milling as an intermediate post-process step between deposition and finishing process, the total processing time was only 22 minutes. So, the conclusions. DED produced a roughness and irregular surface contributed by the presence of adhered particles and bed profiles. The irregularities of the outer layer were completely removed by milling, reaching nanoscale surface roughness, with typical cutting edge marks on the surface. Milling marks were removed by MAF, further reducing roughness values. The whole sequence time for the production of a polished surface involving DED, milling, and MAF was near 22 minutes. Compared to a research article with no milling, the time would be around 5 hours and a half. Milling, used as an intermediate process step between deposition and finishing process, have proven efficient in reducing the overall processing time in the manufacturing sequence of parts obtained by additive manufacturing technologies. Here the reference used in this presentation. My acknowledges to Lapras, Papesp, and Blaser. Thank you. I now open to questions. Please keep safe.